All right, so I would like to thank the organizers for providing me this opportunity to speak about my research. I would like to thank all of you for your interest. I will be speaking about hyperbolic three manifolds with polyhedral boundary. So I start from the motivational part behind my research. And the main source of motivation is the following classical theorem of Alexandrov, which completely describes the intrinsic geometry of the boundary of complex polyhedra in the three-dimensional Euclidean space, and furthermore, in all Riemannian spaces of constant curvature. So this description is that the induced intrinsic metric on the boundary is what is called convex Euclidean conmetric. So I will give a definition. So a Euclidean conmetric on the surface is something that is locally isometric to the Euclidean plane, except a discrete set of points. So when surface is compact, except finite set of points, which I refer as vertices. And at vertices, the metric is locally isometric to a cone with angle distinct from 2 pi. And we will be saying that the metric is convex if all cone angles are smaller than 2 pi. All right, so that's an intrinsic way to think about what is Euclidean conmetric, but the way I'm thinking about it normally, and the way that I suggest you to think about it, is as something glued from Euclidean polygons. So for instance, from triangles, so we have finitely many triangles, and we are identifying edges of equal lengths. So in order to obtain some surface, okay, so I have no clue what's the topological type of the surface, but this is something. So, okay, the point is that it is something glued from Euclidean polygons, or in spherical or hyperbolic geometry from spherical or hyperbolic polygons, respectively. But an interesting thing to keep in mind is that if you have such a metric on your surface, then generically it admits infinitely many geodesic triangulations. So there are infinitely many to represent a single metric in this way. All right, so Alexandrov, this notion, it is designed in order to describe intrinsic geometry of polyhedral surfaces in three-dimensional space forms. And one of the manifestations of this is exactly this theorem of Alexandrov, which says that every convex Euclidean conmetric on the two-dimensional sphere, it can be realized on the boundary of a unique convex polyhedron in the three-dimensional space, which might degenerate to the double cover of a two-dimensional convex polygon, and the realization is unique up to isometry. So an interesting thing to keep in mind is that the original proof of Alexandrov is purely non-constructive. So basically, you can define any metric like this by a discrete data, by gluing of Euclidean polygons. So you can define it explicitly by finite amount of data and by ask, okay, but what can be an algorithm in order to construct such a polyhedron realizing it? And this is totally not possible to obtain from original proof of Alexandrov, but there were further works by students of Alexandrov Volkov, and more recently by Babenko and Izmestiev, which provide a variational approach to this problem, and they can be implemented as a numerical algorithm to actually construct such a polyhedron. So the approach of Babenko and Izmestiev, it was implemented in the computer program. And there are actually two statements in this theorem. One is realization statement about the existence of such realization. And another one is the rigidity statement, is the statement that the realization is unique. Those are actually quite two different statements. So they are definitely interconnected, but you are proving them separately. And it is also nice to keep in mind. All right, and Euclidean conmetrics, so generally conmetrics, they found much more applications here rather than just description of intrinsic geometry of polyhedral surfaces. So they appear when you are studying modulus spaces of some smooth objects on Riemann surfaces. They appear in the study of discrete conformality. So that's a very interesting object to study. And this result is a polyhedral counterpart to the well-known result from differential geometry, which is called the Weyl problem. So the Weyl problem says that every smooth Riemannian metric on the two-dimensional sphere of positive curvature can be realized on the boundary of a unique optoisometry, smooth, strictly convex body in the three-dimensional Euclidean space. And similarly, there are also similar statements in spherical and in hyperbolic geometry. Okay, it was obtained in collective efforts of plenty of people, so I put here just few main contributors, but this list is not exhaustive. And so here the distinction between realization part and the rigidity part is maybe even, so it may be even bigger, because some people on this list, they contributed either to the realization part or to the rigidity part. But I think that more or less it's only Pogorelov who kind of contributed to both, at least to my prior knowledge. All right, and so those statements, they look very similar one to each other. So it's natural to expect that there can be a common generalization of them. And indeed, in the works of Alexandrov Pogorelov, there was obtained a common generalization. So Alexandrov was interested in finding a complete intrinsic description of the induced metric on the boundary of any convex body, which might be neither smooth but nor polyhedral. So like if you have a convex surface which is probably not smooth but not polyhedral, you can still define induced intrinsic metric. So the distance between any 2 points is the infimum of the lengths of all the rectifiable curves connecting them, and it's a well-defined distance on the boundary of any convex body. And Alexandrov found a complete description of it, which is now called CBB0 matrix. So I'm not going to give a definition, but this is the first appearance here of what is nowadays known as Alexandrov spaces, which were further heavily popularized by Gromov as limits of Riemannian manifolds with curvature bounded from below. And Alexandrov and Pogorelov proved that that's indeed a complete description of the intrinsic geometry of the boundary of convex bodies. So every such metric on the two-dimensional sphere, it can be realized on the boundary of a unique convex body in three-dimensional Euclidean space. All right, yeah? Yeah. No, the point is that smooth version, it follows from the most general version, but you need some additional results. So smooth version, so general version, it also shows, yeah, that smooth metric can be realized. But then the question is that if the realization is smooth, and to show that smooth metrics admit only smooth realizations, it's another complicated result of Pogorelov. Yeah, but altogether, from this general theorem and from this result about smoothness of realizations of smooth metrics, another proof, yeah, of the Weil problem follows. All right, so the other source of my motivation is theory of hyperbolic three manifolds. So Thurston famously highlighted, yeah, the importance and the diversity of the class of hyperbolic three manifolds, of hyperbolic manifolds among three-dimensional ones. His work, yeah, on the geometrization program attracted a lot of attention to hyperbolic three manifolds. And for me, the most important feature of hyperbolic three manifolds in my talk is their rigidity. So particularly in dimension 3, it can be formulated as follows, that if you have a closed hyperbolic three manifold, then the hyperbolic metric is unique up to isotopy. So it's essentially unique. But for the scope of my talk, I will be mostly dealing with the following class. So until the end of my talk, M always will be a compact oriented three-dimensional manifold with non-empty boundary consisting of surfaces of higher genii, and I will consider those manifolds that are hyperbolizable. So what's hyperbolizable here? Different definitions can be given. For instance, its interior can be endowed with a complete hyperbolic metric. And that I restrict the boundary only to surfaces of genii at least 2, it's not really a restrictive thing, yeah, because spheres cannot appear, yeah, and if you want boundary to be convex, so if you want to be able to put a hyperbolic metric on such manifold, which is non-complete and which extends to the boundary so that the boundary is convex, then tori also cannot appear as boundary components. And Another thing that it follows from the works of Thurston that this class of hyperbolizable three manifolds like this, it has very easy purely topological description, which somehow shows that this property of being hyperbolizable is generic. So an arbitrary compact three manifold with boundary like this, yeah, it's hyperbolizable. So it's a very interesting class to study on its own. But also, even if you are interested just in closed three manifolds, yeah, but in low-dimensional geometry and topology, there are many things which are done by cutting and pasting arguments. So it's unavoidable, yeah, that people are studying theory of closed three manifolds and three manifolds with boundary in parallel. And you can consider many interesting geometric problems about this class of manifolds. For instance, you can still formulate the Weyl problem for manifolds like this. And the Weyl problem for manifolds of this type, it was resolved, yeah, in works of François Labourie. So François Labourie proved the realization part in the smooth setting that if you have manifold like this, and you are prescribing on each boundary component a smooth Riemannian metric of curvature greater than -1, then Labourie proved that it can be realized by a hyperbolic metric on our manifold. So it's an incomplete hyperbolic metric which extends to the boundary, making the boundary smooth and strictly convex. And later on, Jean-Marc Schlenker established that such a realization is unique up to isotopia. So that, yeah, from the rigidity of closed hyperbolic three manifolds, and because we know, yeah, that convex bodies in hyperbolic space are rigid with respect to the metric, it's natural to expect that when we have a hyperbolic three manifold with convex boundary, then its geometry is determined by its topological type and by the geometry of its boundary. And indeed, in the smooth setting, that's the content of those two results, that yeah, the geometry is determined, and every metric satisfying this natural necessary condition, it can be realized. Yeah, so by hyperbolic metric, yeah, making the boundary convex. All right, so in model spaces, such results, they go in parallel in smooth setting and in polyhedral setting, and the purpose of my talk, yeah, is to report about polyhedral counterparts to those statements. So up to now, the only known polyhedral counterpart, yeah, so we also can define what is polyhedral boundary in this setting. I will do it just later on. The only known polyhedral case was shown by François Fillastre, who proved a polyhedral version, yeah, in the topological case, when you have interval bundle over surface, yes. Yeah, so if you want an example of a manifold like this, that's the best example to keep in mind. So just an interval bundle over surface. Yeah. So François proved an analog of those theorems for polyhedral boundary in this topological case, and also with an additional geometric condition. So there is an isometric involution changing the boundary components. So under this condition, you are prescribing basically not two metrics, yeah, but only one metric, the same from both sides. And if such an isometric involution exists, it means that such a manifold contains a totally geodesic embedded surface, yeah, which provides a very convenient system of coordinates to work with. All right. But the point is, yeah, so the point is that when we are trying to approach polyhedral counterparts of those results, so that, like, what we should prescribe at the boundary, yes. Yeah, so it seems totally reasonable, yeah, that we need to be prescribing convex hyperbolic metric on every boundary component. But it turns out that they have some realizations which are not really polyhedral and which are much more complicated to work with. And also, the techniques that were used in the proofs of those results, yeah, they are very specific to the smooth setting. So I spent quite a while on trying to adapt them to polyhedral setting, but it did not really work well. But then another arguments turned out to be working. All right, but before moving to the results, I need to mention yet another source of motivation. The source of motivation is convex compact hyperbolic three manifolds. So I will quickly recall what they are. So first of all, if I have a hyperbolic manifold, yeah, then I said then I say that a subset is totally convex if it contains every geodesic segment between any 2 points of the subset. So I just remarked that under this definition, if the topology is non-trivial, then point is not a totally convex subset. Point is not a totally convex subset because not from any point here in a trivial topology, there are plenty of geodesic loops. Geodesic loops from point to itself, and any totally convex subset must contain them all. So any totally convex subset, it kind of contains all the topology of our manifold, yes. So like it's always a retract of our manifold, and in 3 dimensions. So in non-degenerate cases, it's always homeomorphic to a compactification of our manifold. Then convex compact manifold is an open hyperbolic string manifold. So I recall that open is non-compact without boundary. It's complete and it contains a compact totally convex set. So this is what is called convex compact. So convex compact hyperbolic string manifolds, they appear very naturally in study of hyperbolic string manifolds with boundary. Particularly when boundary is convex, then there is always a canonical way to embed such a thing, such a compact thing with convex boundary into a convex compact hyperbolic string manifold. So you are just kind of extending your hyperbolic metric beyond the boundary. Another thing that convex compact hyperbolic string manifolds, they naturally appear in study of Kleinian groups. So Kleinian groups are discrete subgroups of the groups of the group of isometry of 3-dimensional hyperbolic space. So that's a very classical topic to study discrete subgroups of Lie groups, and Kleinian groups are the main source of examples. And so one of the first things that you are doing, there are Kleinian groups which are lattices, so that the quotient over them is a closed manifold. But there is a huge source of finitely generated Kleinian groups such that the quotient is not compact. But those things, when the quotient is convex compact, they are generic. They are generic. So if you are fixing a Kleinian group and looking for the deformation space, which is a very interesting topic, then the interior of this deformation space, it will correspond to convex compact hyperbolic structures. So, and for other thing, if you are fixing topology and you are considering all complete hyperbolic metrics that you can put on this topology, so it's a very interesting moduli space, and its interior corresponds to convex compact hyperbolic metric. It also has a very rich and very non-trivial boundary. Sorry?
The right one is complex compact, it's not a complex compact is something for a group.
Okay. In this sense, it's truly, but I just inherit this terminology from Kleinian groups, but that might be a fair remark. But it's just a matter of terminology. Sorry? No, what is your question? One point, when the topology of manifold is non-trivial, one point is not a totally convex set. Because there are plenty of geodesic loops from point to itself, and any totally convex subset, it must contain all those geodesic loops. So point is not a totally convex subset. So for instance, sorry? No, it should be compact because there are some examples of open hyperbolic string manifolds which are topologically tame, but which are geometrically infinite, and there is no compact totally convex subset. All right. So it's a very interesting topic to study convex compact hyperbolic string manifolds, and a very important object there is the convex core. So the convex core is defined as the inclusion minimal totally convex subset of our manifold. So from this definition, it's not really clear if it is well defined, but I just recall that if you consider the universal cover of a manifold, yeah, and associated, so it's complete, so the universal cover can be associated with all three-dimensional hyperbolic space, then the holonomic representation is a Kleinian group, and it has limit set at infinity, and if you take the convex hull of a limit set, then it's invariant under the group action. If you project it back to the manifold, that will be the convex core. And the point is, so that the geometry of a convex compact hyperbolic manifold, it's well understood outside of convex core. So, so basically, such a manifold can be thought as the convex core and several pipes where the metric expands to infinity. And so in those pipes, they can be conformally compactified. So they have natural conformal boundary at infinity. And they admit foliations, very nice foliations by constant mean curvature surfaces, by constant Gaussian curvature surfaces. And one can say that their geometry is well understood. So what is geometrically, what is much more geometrically complicated is the convex core. So Thurston made an interesting observation that if you look at the convex core, and if you, so its boundary is convex, but it might be neither smooth nor polyhedral. Anyway, you can define the induced path metric on the boundary of convex core, and Thurston observed that equipped with this induced path metric, the boundary of convex core consists of finitely many hyperbolic surfaces. So those surfaces, they are isometric to hyperbolic surfaces. So intrinsically, the metric is smooth, but its embedding in our space may be heavily non-smooth. So it can be bent along what is called bending lamination. So bending lamination, it might be just finitely many simple closed geodesics. And so it might be a hyperbolic surface, which is totally geodesic outside this set of bending lines. And here you have some non-trivial dihedral angles. But it also can happen that this bending lamination is supported by uncountably many of open disjoint geodesics. So they are open, they are disjoint, and there are uncountably many of them, so they are winding around each other in some sophisticated manner on this surface. Yeah. So neither case is really generic. So if you look at the space of measured laminations, which are the objects that are describing what those bending laminations are, then there are measured laminations that are supported on rational laminations. So rational laminations are those where the support is finitely many simple closed curves. They are everywhere dense, and also those that are supported on irrational laminations. So irrational laminations, like are described in the end, they are also everywhere dense. So this is some way how to describe how the boundary is bent in the setting, even though it might be not really something polyhedral or smooth. All right, so that's a very quick recap of theory of convex compact hyperbolic three manifolds. And so, as I told you, for instance, it's a very interesting problem to fix topology and then to describe the moduli space of complete hyperbolic metrics on it. Convex compact hyperbolic metrics, they constitute the interior of it. So the first task is then to describe interior, and it was done well. So in a long string of efforts of plenty of people. So as I told you, convex compact hyperbolic three manifolds, they can be conformally compactified by adding Riemann surfaces. And in a long string of efforts, it was proven that every conformal structure can be realized at the boundary at infinity by a unique optoisotopic convex compact hyperbolic metric. Okay, but so in the study of hyperbolic three manifolds, a big part of it is given by complex analytic techniques. Yeah, because the boundary at infinity of the hyperbolic three space, it's the extended complex plane. So many things can be done from complex analytical perspective. And this is one of the instances of it. This is one of the instances because basically that's a result belonging to the domain of complex analysis. And a very interesting direction of research is understanding how properties of this parameterization are related to actual geometry of our hyperbolic three manifold. And on some side, it would be interesting to have a more geometric parameterization of this moduli space. And it was conjectured by Thurston that it can be done by the induced intrinsic matrix on the boundary of the convex core. That, okay, if you look at the boundary of convex core, then every hyperbolic metric on every boundary component, you can prescribe a hyperbolic metric on every boundary component, and it can be realized by some convex compact metric, and that this metric is unique up to isotopy. So the realization part follows from the work of Labourie, but the rigidity part is open, and there is a dual conjecture that allows to describe the space through the bending structure, of the boundary. So the bending lamination is an instance of what is called measured lamination, and not every measured lamination can be realized as a bending lamination of a convex compact hyperbolic structure, but there is a notion of admissibility, and so the conjecture is that every admissible measured lamination can be realized as a bending lamination for a unique up to isotopic convex compact hyperbolic structure on our manifold. And once again, the realization part was proven. It was established in the works of Bonachon et al. And of Lecquier. There was some progress also on the rigidity part. So Bonachon et al. Proved the rigidity in rational setting. Bonachon also proved the rigidity near the Fuchsian locus, but outside of this, the rigidity is also open. All right, so I finished with the motivation, and now I can formulate the results. So, but in order to formulate the results, I need to introduce few definitions. So, first of all, okay, I will be speaking about hyperbolic three manifolds with polyhedral boundaries. So first I want to define what is actually a polyhedral boundary. So I think the most natural way of defining it is by means of local modeling. So boundary is polyhedral if it can be locally modeled on polyhedral sets in three-dimensional hyperbolic space. So this is what is written here. So that's the most natural way to define what is polyhedral boundary, but one needs to be careful. So, and actually, if one wants to work with the Alexander-Vail problem in the setting, then it turns out that one has to generalize this definition, further to what I call band boundary. So in all the settings here, we have an incomplete hyperbolic metric on our manifold that extends to the boundary, making the boundary locally convex. And I say that the boundary is band if every boundary point except finitely many belongs to the relative interior of a geodesic segment, and here geodesic segment in extrinsic sense. So it should be really just a segment of a hyperbolic line. So what's the point? The point is that if you consider this definition, so if you consider a closed surface in three-dimensional Euclidean space satisfying this definition, then it will be actually a polyhedron. So that's an easy exercise. Yeah. And so it's not really something special about Euclidean geometry. It's more something special about simply connected settings. So for the hyperbolic three-dimensional space, it will be also the same. But when you have non-trivial topology, then those definitions already turn out to be different. And an example of it is the boundary of convex core. So the boundary of convex core, when it is bent along irrational laminations, it is something that satisfies my bend condition, but it does not satisfy my definition of polyhedral boundary. So they turn out to be different. But anyway, when you have band boundary, I can prove that the induced intrinsic metric is always a convex hyperbolic cone metric. And in order to formulate my results, I also need to introduce two subclasses of polyhedral metrics. The first thing is strictly polyhedral. So if you have convex boundary, then you always have already a convex core inside. And I say that the boundary is strictly polyhedral if if my boundary does not touch the convex core. If it does not touch, then it's strictly polyhedral. And I would say that it's controllably polyhedral if the boundary is polyhedral, and either it does not touch the convex core, so then it is strictly polyhedral, or the intersection is one-dimensional. And I can show that when intersection is one-dimensional, then it is just finite many of simple closed geodesics. Okay, so I now gave those notions in terms of their naturality as I perceive it, but now I just rearrange them. I just rearrange them in terms of their generality. So band boundary is something most general in this context. Then polyhedral, yeah, is something stricter. Controllably polyhedral is something stricter, yeah, and strictly polyhedral is the most stricter, yeah, but no two of them are equivalent. All right, so now I can formulate my main statement. So it's the following one. So I have a manifold M as before, any hyperbolizable compact-oriented three-dimensional manifold with boundary of higher GNI, and I'm prescribing a convex hyperbolic metric on every boundary component. Then I can prove that it can be any such metric can be realized by a band hyperbolic structure on the ambient manifold itself. And if the realization is controllably polyhedral, then this realization is unique up to isotopy in the class of band metrics on M. Okay, so this might look slightly cumbersome, so I'm going to clarify the roles of classes of metric here. Okay, so convex hyperbolic metrics is with what we start. So when we try to prove a polyhedral analog of the Alexandrov-Weyl problem in this setting. Okay, so band metrics on the manifold itself. I claim that the class of band boundaries is the right class to work here, because as I told you first, I can show that if I have band boundary, I can prove that the induced intrinsic metric is exactly convex hyperbolic metric. And furthermore, I can show that if I have any hyperbolic structure on M with convex boundary, and I know that induced intrinsic metric is convex hyperbolic metric, then I can prove that the boundary is band. So band is something about how boundary is curved in ambient space. Yeah, so I can show that this is always the case. So band boundaries is really the correct class here to work. Okay, then I need to say about controllably polyhedral boundaries. So how does this class appear actually? So actually the initial motivation behind my research was to prove rigidity in the strictly polyhedral case. So I first expected only this. Why? Because if we return here to the motivational results, then here is condition that the curvature is strictly bigger than -1. And actually, strict condition is quite important here, because the techniques essentially quite break down when the inequality can be non-strict. And the thing is that strict inequality here, it means that the boundary cannot touch the convex core. So it implies that the boundary cannot touch the convex core, and this is very important for the proof line, particularly for the proof line of rigidity. And kind of a polyhedral analog of this is strictly polyhedral boundary. Strictly polyhedral boundary when the boundary cannot touch convex core. Yeah, but when I was trying to prove rigidity for strictly polyhedral boundaries, it turned out that I actually have to expand the class under consideration to controllably polyhedral ones, because I could not really prove without extending the consideration to this, but it is nice here because anyway, it's a bigger class. Sorry? For convex boundaries, no, and they are not expected. Yeah, but like for non-convex, you can always turn something in the opposite direction. Yes, so that when you have non-convex boundaries, yes, then you cannot expect global rigidity. Yeah, but for convex boundaries, so it is expected, yes, that just any convex boundary, it completely determines the metric inside. The metric inside the manifold, yeah, but it is shown, yeah, only under some additional conditions. Okay, so another thing here is that it's not really clear. It might be not really clear how many convex hyperbolic on matrix have controllably polyhedral realization. So how good is this rigidity statement? So I claim that actually this is a generic case. This is in some sense a generic case. So I say that a hyperbolic on metric is balanced. So a hyperbolic on metric on the boundary of M is balanced if the set of vertices is sufficiently dense. So I'm not going to say what's sufficiently, but that's the heuristic behind the definition. And under this definition, the set of balanced metrics is open and dense among all hyperbolic on metrics equipped with the Lipschitz topology. And I can show that for any balanced con metric, any its band realization, and because of the second theorem, every convex realization is necessarily controllably polyhedral. So in this sense, it is a generic case.
You are not assuming boundary.
No, I'm not assuming incompressible. Yeah, it works both in incompressible and incompressible cases. Yeah. Yeah. All right. And so another outcome is a partial progress towards conjectures of Thurston. So I can show the following. If I fix topology, so if I fix some topology and I consider all convex compact hyperbolic metrics up to isotopy, then I can show that there exists a big open subset. So this subset, it contains all metric with polyhedral convex cores. So if Thurston's conjectures are true, then this subset is dense. But the density of the subject, yes, so it depends on the resolution of the whole conjectures. And I can show that metrics, convex compact metrics in this subset, they are uniquely determined by the induced intrinsic metric on the boundary of the convex core, and they are infinitesimally determined by the band denominations. All right, so now I formulated all the results, yeah, and I want to speak a bit about the proof techniques. Yeah. Yeah, band along rational lamination. All right, so the general framework is quite traditional for results like this. It is the continuity method, which was in context of discrete geometry heavily popularized by Alexandrov. So we are fixing topology, so we are fixing some M, we are fixing some finite set, and we are denoting the space of convex hyperbolic on matrix on the boundary with vertices marked by the set up to isotopy. And we are denoting like this the space of band hyperbolic matrix on the three-dimensional manifold M with vertices marked by V, once again up to isotopy. Okay, so those are some finite dimensional topological manifolds, and we have a derealization map. So like we want to realize every such metric by band structure on M. So we are considering every band structure and associating to it the induced metric on the boundary. So then we are working with the properties of this map. So the first thing is that we are showing that over the subset of the thing of controllably polyhedral matrix, this map is differentiable. Okay, so a funny thing that I cannot prove that it's continuously differentiable. So the differential is continuous over strictly polyhedral matrix, but for controllably polyhedral matrix, I cannot prove the continuity of differential, but it turns out that I do not really need it. So another thing is infinitesimal rigidity, that the differential of this map is non-degenerate. So altogether, even without the continuity of the differential, it gives us that this map is a local homeomorphism. It's local homeomorphism, but I highlight that only on some subset of the thing. So only on the subset of controllably polyhedral matrix. Then we show that this map is proper. So if we knew that it's differentiable and the differential is non-degenerate everywhere, then it is known that this space is topologically a cell. So then it would be a homeomorphism. But we cannot really conclude it. We cannot really conclude it easily because we can show that it's local homeomorphism only over some subset. But with the help of some topological arguments, we can show the realization part, and we can show a transition from local rigidity to global. So this is the general framework. And in the remaining time, I want to speak here a little bit about the most interesting part of it, the infinitesimal rigidity. Okay, so here are two main complicated steps. So first complicated step is differentiability, and second complicated step is infinitesimal rigidity. Yeah, so Okay, for instance, the next step here would be to prove rigidity for polyhedral boundaries, so not necessarily for controllable polyhedral, but for polyhedral boundaries. And an interesting thing that for them, I know how to prove infinitesimal rigidity, but I cannot right now show that the map is differentiable, for polyhedral boundaries. Okay, so in the remaining time, I will speak a bit about infinitesimal rigidity, how it is done. So it is done with the help of application of infinitesimal rigidity results for hyperbolic cone-3 manifolds. So like I described you here what hyperbolic cone surfaces are, and also there is a similar concept of a hyperbolic cone-3 manifold. So vaguely it can be thought as a gluing of hyperbolic 3 polyhedra. The only thing that in this case, yeah, you need to care about the link of a vertex in your gluing. There is an intrinsic definition of what is a hyperbolic cone-3 manifold, but I am not going to give it, so it's slightly intricate. Yeah, so like the main example that I suggest you to think about is just to take a convex hyperbolic 3-dimensional polyhedron and double it along the boundary. So you will already obtain a nice example of a hyperbolic cone-3 manifold. So cone-3 manifolds like this, they seemingly were first considered by Volkov, a student of Alexandrov, in his quest to give a variational proof of the Alexandrov theorem. Then they were rediscovered by Thurston, and a lot of applications in low-dimensional geometry and topology were found. So the hyperbolic Dunn-Filling theorem was proven with the help of them. One of the approaches to the density theorem for the Kleinian groups was with the help of them. So they were used in the geometrization of 3-dimensional orbifolds, in some works on discrete conformality. And in the scope of my talk, yeah, and in general, one of the main things about them is the rigidity of them, in the closed case. So if you have a closed hyperbolic cone-3 manifold with some convexity condition that cone angles along the singular set are smaller than 2 pi, then they are infinitesimally and locally rigid with respect to the cone angles. So it means that locally the geometry is determined by the topology of our manifold, by the topology of singular locus, and by the cone angles. So conjecturally, this rigidity should be global, yeah, but global rigidity is still not proven in the most general case. All right, so the heuristic approach is more or less the following: that doubling construction, it allows us to relate deformations of hyperbolic 3 manifold with polyhedral boundary that preserves the boundary infinitesimally, and deformations of closed hyperbolic cone-3 manifold. Because we have a manifold, a hyperbolic 3 manifold with non-empty polyhedral boundary. We take 2 copies of it, and suppose that we have a break in infinitesimal rigidity. So we have a variation of metric that infinitesimally preserves the boundary. Then we can consider one copy deforming by this deformation, another copy determined by this deformation. And heuristically, because they induce, they infinitesimally preserve the boundary, you can glue those 2 deformations together to an infinitesimal deformation of the double. And because we are deforming one component along tangent vector and another component along minus this tangent vector, they induced infinitesimal changes on all the angles, of the edges of the boundary. They get compensated. On the gluing. So heuristically, we should obtain an infinitesimal deformation of the double, which is closed hyperbolic cone-3 manifold. Okay, but there are some problems with this heuristic. So the first thing is, what does it mean? What does it mean to glue together 2 infinitesimal deformations? What does it mean to glue together? So like a naive approach would be, okay, let's consider one parametric path tangent to this vector, yeah, and let's just glue those things together along this path and then differentiate them as cone manifolds. But the point is that if we have a break in infinitesimal rigidity, it does not mean actually that we have necessarily a break in local rigidity, so that we cannot really glue them along this path. But what is even more disturbing is that combinatorics of the boundary can change. So in this case, actually, when we are considering controllably polyhedral boundaries, then there are some faces that are not simply connected. And locally, there are infinitely many of possible combinatorics. So normally when you work with polyhedral geometry, then you are considering your configurational space of some polyhedral thing, and you are dividing this configuration space into cells corresponding to different combinatorics. And normally, this decomposition into cells is locally finite, but in this case, it's not. In this case, it's not. There are some things in the deformation space, but when there are infinitely many combinatorics, and you're moving along the path, and your combinatoric just immediately starts to change, and it changes infinitely many times. So like any such deformation, it might even infinitesimally change the combinatorics, and then those results are formally non-applicable because they work only for fixed singular locus, only for fixed topology of singular locus. So in order to find a resolution for this, we need to think slightly more about infinitesimal deformation theory of cone manifolds. So I will just quickly recap how it happens in this situation. So we have a closed hyperbolic constraint manifold with some singular locus, and we have a smooth part. So L is a smooth part of it. And so deformations of hyperbolic cone structures, they are a particular case of deformation of the hyperbolic structure on the smooth part. And it is known that up to some natural equivalence via the holonomy theorem, they are associated with the deformation of the holonomy map of our structure. So the first thing is to have a look at the deformation theory of the holonomy maps. So we have the space of representations of our fundamental group in the group of isometries of three-dimensional space. We take its quotient modulo conjugation, and the Zariski tangent space, here it is described by the first homology group of this fundamental group with coefficients in this model. So this model is just the Lie group, which is considered as a G model, as a P1L model through the composition of our holonomy map and the joint representation. Yes, so this is a very standard construction from in representation theory, so in theory of geometric structures. It was also mentioned by Franceschi in his talk. But there is a more convenient way to work with it. A more convenient differential geometric way to work with it is to work with the bundle of infinitesimal isometries. So we are considering the universal cover of our singular, of our smooth part. Yeah. So we have a closed hyperbolic cone manifold. We are throwing out the singular locus. We are looking at the universal cover, and we are considering just direct product of this with our Lie algebra. And we consider the action of the fundamental group on it. So on the first component, we act just by deck transformations. On the second component, we act through our representation. Then we are obtaining quotient bundle. So it's kind of a twisted bundle of infinitesimal isometries over our manifold A. And so there is an analog of the RAM theorem in the setting, which says that the first cohomology group of this bundle is the first cohomology group of our fundamental group, with coefficients in this model. Okay, and I maybe forgot to say that we know, that the whole representation space, it's an algebraic variety with some singularities, and the group action by conjugation, is not nice globally. But the point is that it is a part of the theory of infinitesimal deformations of cone structures, that when we have a cone structure, then the respective holonomy, it belongs to the smooth part of the thing, And so if you consider a neighborhood, on this neighborhood Gx nice, so we might not think about really about algebraic geometry, about any singularities coming from algebraic geometry and from not nice action of G. So like we are right now interested in things only locally, and locally everything is nice. Okay, so and there is yet another way to look at it. Another way is to look actually through vector fields on the universal cover. So if you have a geometric structure, then it gives rise to a developing map and a holonomy map. And a deformation of geometric structure, it will be a vector field. A vector field on the universal cover, it will give a vector field on the universal cover, which is, however, probably not equivariant. So it doesn't descend to a vector field over our manifold L, but it satisfies this automorphicity property. So if you consider any element of the fundamental group, and we are considering pullback of our vector field minus our initial field, then it is a killing field. which is determined by gamma, but which might be different for different gammas. Okay, and a special feature of dimension 3, so is that if you consider the space of all automorphic vector fields modulo trivial ones in this context are equivariant on Killing vector fields, then the space is isomorphic to this this vector space that we defined previously. Okay, so those are 3 ways to look on it, and actually when you are working with infinitesimal deformations, it is quite worth to keep all 3 of them in mind. And the infinitesimal rigidity of hyperbolic constraint manifolds, it is normally formulated in this language. So it is shown that when you have a deformation that preserves the cone angles, then it can be represented by L2 differential 1 form. And another part of the proof is to show that the first L2 cohomologies of this bundle are trivial. So in this situation, they are trivial, and this is actually another way to reformulate the infinitesimal rigidity of hyperbolic constraint manifold. Yeah, so then what do? We are considering our manifold with polyhedral boundary, and we want to triangulate it. We want to triangulate it, so to a 3-dimensional triangulation into simplices. A funny thing that I don't know how to do it in general, but I can prove that there is always some cover, some finite cover, which can be triangulated, and it is enough for our purposes. So assume that we can triangulate, and that we have a break in infinitesimal rigidity. So then I claim that for every boundary edge of my triangulation, the induced infinitesimal deformation is 0. This is actually a non-trivial statement. This is a non-trivial statement because this length of this edge of triangulation is not the same as the length of respective segment in the boundary. So they coincide at the initial part, but when we are considering any one-dimensional path in our configuration space, then the boundary immediately might become non-convex, and this triangulated complex, it's possibly along any one-dimensional path, it stops coinciding with our manifold. This happens exactly when combinatorics changes. And there are a lot of situations here when combinatorics changes really drastically. But still, we can prove that actually the break in infinitesimal rigidity, it means the break in infinitesimal rigidity of the boundary edges of our triangulation. Yeah, but this is quite a long computation, actually. And the point of, one of the main points of the proof of infinitesimal rigidity is that, okay, we now have a triangulated complex, and we have infinitesimal deformation of it, which induces 0 deformation on every boundary edge. So we are taking 2 copies of it, we are gluing them together and considering on one copy one deformation, and on other copy minus this deformation. So we have deformations of all edges. But this is not really connected with infinitesimal theory of hyperbolic constraint manifolds. So in order to connect them by this infinitesimal deformation of the triangulation, we are constructing an automorphic vector field on our double of some special form. And then through the duality, we are showing that this automorphic vector field corresponds to some differential 1 form. Then through properties of our construction, we show that this form preserves the angles, and that's why it's trivial by the works on infinitesimal rigidity of hyperbolic constraint manifolds. Yeah, so that we can conclude the infinitesimal rigidity. Yeah, and I am actually finished right now. Yeah, so I will. So I finished. Yeah, I finished what I want to say about infinitesimal rigidity. So there are some directions for further research which you can ask me about if you are interested. But I finished right now. So thank you for your attention.